My name is Greg Gabadadze. I'm the chair of the physics department at NYU. On behalf of the Dean for Science, Professor Michael Puruganan, and the Department of Physics, I would like to welcome you all to this event. There are times in human history when breakthrough developments take place in arts, science, technology, or fields of pure thought. Those developments leave incredible legacies that eventually shape human lives one way or another. Such were times when perfect forms of arts were unveiled by Da Vinci, Michelangelo, and others, and new continents were discovered by Columbus and his followers, as were times when laws of nature began to be systematically uncovered by Galileo, Kepler, Newton, and other colleagues. We seem to be living in an exciting period when new planets orbiting stars other than our sun are being discovered. These are new worlds full of surprises and different type of beauty. The discoveries of these planets, the so-called exoplanets, are being done by a small group of superstars. And today's speaker, Dr. Sarah Ballard, belongs to that elite group of scientists. Sarah got her PhD from Harvard University in 2012. Currently, she holds a prestigious NASA Carl Sagan Fellowship at the University of Washington. In spite of her very young age, she is a recipient of a number of awards and grants. Today, Sarah is going to tell us about wonders of taking the M79 bus across the Central Park and the new world that the ride opens up. Please join me in welcoming Dr. Sarah Ballard.
Thank you so much, Greg, for that wonderful introduction. Can you hear me in the back if I speak at this volume? Okay, thank you. So I thought I would open my talk with an image that speaks to the very provocative title that I used. So I usually start Exoplanet talks for audiences of non-scientists by asking if there was anyone born after 1995. I'm guessing maybe not in this audience. I was doing kind of a once-over before. But in audiences of students, you know, this is the age of a college freshman. Many students raise their hand. And this is the year that the first exoplanet was discovered. So I'll admit to you, I was born in 1984. It was fully 11 years that I was on the Earth when humanity did not know about any planets outside of the solar system. It was sort of unclear whether we existed in an island of life, you know, in a barren universe. This question is still one which is unanswered, but it began to be answered in 1995, coincidentally the year of Carl Sagan's death, with the discovery of the first world orbiting another star. And this world was not eminently habitable in any way. A Jupiter-sized world, you know, a swirling ball of gas, 10 times the radius of the Earth. It doesn't have a solid surface on which creatures might walk. It was much too hot to be amenable to liquid water, and yet it was something. And I want to comment on what an incredible time it is to be alive, so especially for these college freshmen now. They've never lived on the planet Earth at a period of time that we didn't know there were worlds around other stars. And yet for a very long period of time, from 1995 to sort of 2009, was a period of time in which the universe of small planets was still opaque to us. And this had to do with the fact that these small rocky planets are very hard to find indeed, not because they don't exist. And so since 1995, for reasons I'll tell you about, we know a great deal more about planets, and something very suggestive. And usually in public talks about exoplanets, I get the question, is the solar system like other systems of planets? You know, are we drawn from this overall distribution of planets? Are we very close to the middle? You know, and scientists used to hedge at the answer to this question. Oh, perhaps the answer is yes, perhaps the answer is no. We wouldn't know because if we were alien beings looking in on our own solar system with our current technology, we would not have yet detected the Earth. You know, and so this is a question we can't answer. Well, now we know the answer because the vast majority of planets, indeed the smallest planets, orbit stars which are nothing like our own sun. So now we can say for a fact, actually, that the solar system is unusual. This is something that keeps me up at night. Why are we orbiting a rock around a sun-like star? It's quite odd, actually, given that most of the small planets are orbiting stars very dissimilar from the sun. And so I'll kind of walk through how far exactly. So, you know, this was not a fruitful search in Google Maps. You can see I put public transportation too. It's not, it's not currently, but I'm going to make the case, you know, and you can apply to me in 10 years, that I'm going to make the case, I'll bet you, that within 10 years period of time, we will indeed know the address of this planet. We don't know it today, but I can promise you that it's there. And the reason for that is because of a singular NASA mission, and I'll sort of be telling you the story about that mission. So it all has to do with how we detect planets around other stars. That first planet detected in 1995 was not using the means that I'll be describing, the vast majority of detections in this talk, but this detection method is one of the richest. And it's sort of for the following reason. So this star is one that's very near and dear to my heart and all of your hearts. This is our own sun. It was imaged by NASA's Solar Dynamics Observatory. And this is in 2012, the planet Venus, which is the second planet from the sun, transited in front of the sun. By transited, I mean it passed in front of the face of the sun from the perspective of somebody on the Earth. So you can see the planet passing in front of the star. This event took about 10 hours to occur. The Earth is a little bit further back from the sun, and so in order, the period of time that it takes for the Earth to traverse in front of the sun is 13 hours. Well, now that sort of answers the question, why did we have to go to space to see Earth analogs? Because human night is not long enough to observe an event of this duration. In most parts of the Earth, except at the North Pole, the South Pole, in these extreme conditions, we don't get 13 hours of dark, enough to observe the stars to see whether they present these signals of other worlds passing in front of stars. So now this is our own, beautiful sun. You can see how dynamic it is. And amazingly, we've resolved the planet passing in front of the star. But this is possible only for the very nearest star, our own sun. For the vast majority of stars, we are not yet capable of resolving in the sense of actually viewing the planet passing in front of the star. Instead, we have to infer that the planets are there indirectly. And this is what I mean by the transit method. This is planets passing in front of their host star. This is a schematic video produced by the European Space Agency. So now here's another planet passing in front of its star. And you can see all we can do is measure the total brightness of the star. These are pinpoints of light, and yet that brightness is seen to dim as a function of time when the planet goes in front of the star. Based on the duration of this event, we know how fast the planet's moving around the star. Based on how often these events occur sequentially, we can infer the period of the object, how often it sweeps around the star. And based on the transit depth, we can infer how big that planet is with respect to its host star. This is sort of the power of transit, so much rich information from one single event, and yet the first transit wasn't discovered until 2002. There's a professor, he's now at Princeton University, but at the time that I was a graduate student at Harvard, he was there. He specialized in a network of ground-based telescopes which were looking for those planets which were first, so easy to skim off of the top, the hot Jupiter-sized planets. And that was called sort of the HAT network. At the time, these planets, were coming up a few times a year. You would hear about a new planet. Every hot Jupiter was worthy of a publication. Now you can't swing a purse without hitting an Earth-sized planet. But I was a graduate student at this period of time. So when I entered the field in 2007, my first project was on the one known hot Neptune planet. The one, and now there's 1,000. But at the time, everyone who was interested in exoplanets was studying GJ436, GJ436. You couldn't, you didn't hear about any other planet. It was definitely the most popular planet. So what I'm going to show you is this video that Gaspar produced. And he produced it in order to express something about the discovery rates of exoplanets. And in this video, you'll see that something very particular happens in 2009. He called the video the well-tempered exoplanets because in the process of making this video, he wanted to communicate to the audience something about the planets we were discovering based on two qualities that you could hear. The first one is the pitch. Okay, so like a much more massive planet, boom, 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 and a smaller planet, woo, woo, woo. And then the period of the planet would be encoded in how often these sounds occurred. So this is a video I'll play separately, but first I just want to play with Bach's original, The Well-Tempered Clavier, which was the reference if you didn't know about it. So first I'll sort of show you here. So here in comparison, let me scroll away, to sort of orient you to this figure. This is showing the mass of the exoplanet on the x-axis, the radius of the planet on the y-axis, and then these are planets which should look like old friends. Here's Jupiter over here. Overplotted in these green triangles are the planets of the solar system. Okay, so here's Jupiter, here's Saturn, Neptune, and Uranus Earth, Venus, Mercury, and Mars are like over at this corner. They're so small, it would hardly even register on this diagram. Okay, so here's our old friends, the solar system planets. And I'm going to play this video forward in time. You're going to see the year advancing right here. So this is starting in 1999. We didn't know about a single transiting planet. The first one was discovered in 2002, the year I graduated from high school. And I'm going to show you, so the discovery year will advance, and the name of the planet, as it appears on the diagram, will be shown right here. And I'll pause right at 2009. Let me turn off this. So there's the very first one in 2002, or sorry, 2000. Very solitary for a long time. You can see why people were all studying HD 209458. 189733. And then more people kind of got into the game of looking for hot Jupiters. This is all Jupiters, though, and all very hot. Whereas 2007, GJ 436, you can see why it was all anyone cared about down here near Neptune. Now I'm going to pause right here. So here we are in May of 2009. So this is sort of the state of the field. In 2009, I was a second-year graduate student. At the time, this was considered a wealth of transiting exoplanets, and indeed it is, compared to 0. You know, you can see we had a whole body of hot Jupiters. I mean, it was an incredibly exciting time in the field, and like I said, a single new hot Jupiter paper was something that everyone would be talking about. There, you know, why do they exhibit this spread in radii in comparison to their mass? There's sort of a spread in density and so on, and talking about discovering planets which were similar in nature to Earth was still something we would do in 5 or 10 years. So something crucial happened in March of this year, which was the launch of the Kepler mission. I still remember I was a second-year graduate student, and we all gathered in Phillips Auditorium at the Harvard-Smithsonian Center for Astrophysics to watch the live launch of the Kepler spacecraft from Cape Canaveral. You know, and you could see that, you know, if you've ever seen 60-year-old astronomers like holding hands, as this rocket went up, you can see how like tensions were running high among groups of scientists. And it's for the singular reason that Kepler was going to be able to uncover the planets, if they were there, which were different in nature from anything we could see from the ground. So I mean, not only because these planets' transits take so long, because they occur so seldom. You know, if we were alien creatures looking in on the Earth, we would see the Earth present a transit once every 365 days. So you need some single eye paved with silicon that's just staring at the sky, you know, and not blinking for a long enough period of time to see an Earth analog planet, and we simply didn't have that until we went to space with Kepler. So now I'm going to play the video going forward. After the launch of Kepler. And you can see that these small planets are beginning to appear, including these. So it's not that those planets weren't there, we just hadn't discovered them yet. This is sort of the state of the field. The colors. I think in this particular case it's corresponding to the, could it be the, it's not the density, although it does look similar to density. Could be something like density. I'll have to look it up. Yeah, it obviously, so the curves here are corresponding to different densities. You know where densest planets would be down here, the smallest radii, and yet they, you know, they contain the most mass. I stole this video from YouTube, you know, and it didn't say. I'll have to email Gaspar and ask him. So now I'll play it with the actual sound, so you can hear the discovery of these planets, the pitch of the planets. You can see why everyone was paying attention to just this one planet, how easy it is to hear.
What is the little clicking referred to?
The pitch is referring to the mass of the planet. The number of beeps it presents and the frequency of those beeps is corresponding to the period. You can see it's beginning to get, it seemed cacophonous even then. That's a big one. And then, you know, after the launch of the Kepler mission, it's really getting deafening.
Good thing all the planets aren't exactly at the same position in the sky.
Yes. Yeah, right, that would be deafening. Yeah, this is an example, you know. I like this video because it sounds to me like the exoplanets are speaking to us. Of course, they don't speak English. You know, but they're out there to be discovered, and the really amazing thing about the Kepler mission is that hot Jupiters were not so common after all. They were all we could see back then. They occurred around every 1 out of 100 stars, and so people thought, well, maybe only 1 out of 100 stars has planets. Actually, Jupiters are quite rare. Here. So this was the total knowledge of exoplanets in 2008, 23 of the known systems. It used to be in exoplanet publications that you would show every single planet that was known, you know, and that would fit on a page. So this is showing a lot of information about these different planets, the individual transit light curves, by which I mean the brightness as a function of time as the planet passes in front of its star. This is all to scale. So you can see how there's a variety of stars. There's one that's quite strange. You know, this one's much smaller. It was, again, the single known transiting hot Neptune. So even a planet the size of Neptune, Neptune is 4 times the size of the Earth, barely shows up on this diagram. You know, so it was mostly just this wealth of hot Jupiters. So 23 of the 52 known exoplanets. Well, then what happened? And this was published in 2008. The answer is the Kepler mission was launched. So this is an image taken from Cape Canaveral. So the Kepler team got to travel to Cape Canaveral to see it. I wasn't part of the Kepler team at that time. I was a newly minted graduate student. So this is monitoring 150,000 stars for 4 years, basically staring at this single part of the sky and waiting for the telltale sign of a single star to dim by a fraction of a percent, corresponding to a planet passing in front of it. And the thing about transits is, of course, not every star that has a transiting planet will present a transit. Not every star that has a planet will present a transit. Sorry, and the reason for that is because of geometry. You know, most of the planets that are going around their stars aren't going to pass between the line of sight, between our eye or the eye of our telescope and the star. So at the time, I was actually, the Kepler mission was originally launched to observe stars for 4 years. It was approved for an extended mission of up to 8 years. If you haven't read, you know, it was my dad sending me articles in the New York Times. Oh, the Kepler mission was hobbled. It was hobbled. You know, so it started with these 4 reaction wheels, which finally control the pointing of the telescope, and then one failed. And then in May or April of this year, another failed. And then there was kind of a collective cringe from the exoplanet community because Kepler could no longer stare with the precision necessary to look for these telltale signals. There's since now 40 papers from the community on what we can do in an extended Kepler mission, even if it can't point precisely. But the truth is that Kepler, as it used to be, is probably done. But it completed that 4-year mission. At the time that it was launched, I was taking a Japanese class. This is the artist's conception of Kepler. You see, it's a very friendly instrument. This actually says like Kepler rendered in the Japanese syllabary. And so the point of Kepler was that it was a mission statistical in nature. So it wasn't looking at the nearest stars. You know, the question of where is the nearest Earth-sized planet? How do I get there? Which bus do I take on the MTA? It was only looking at a set of stars and asking how common are planets. It was asking what is the so-called Eta Earth? You can't go to any exoplanet conference without hearing Eta Earth at least 100 times. It means the frequency of Earth-sized planets around sun-like stars. How often do these things occur? And it was able only to detect the period of these planets by the nature of the transit signal. It detects the period based on how often that dimming occurs, and it detects the size of the planet based on what fraction of the star's light disappears when the planet passes in front of it. So this is the Kepler point of view. It's overhead in the northern hemisphere around midnight in the summer, and it's about the size of your outstretched hand. You know, so it's staring at 150,000 stars. I wish you could see this a little bit better. Maybe I can. Is this? Nope. Okay. Well, so this is just a close-up of this footprint on the sky. You know, this silhouette on the sky that Kepler was staring at. This single eye comprised of detectors, you know, a single receptor, just paved with silicon, observing 150,000 stars. So remember, at the time that Kepler was launched, we thought maybe 1 in 100 planets had a hot Jupiter. You know, and if every one of those has a 10% probability of transiting, you know, you're probably not going to see very many. But this was the riches that we were rewarded with after 4 years of emissions. This is of January 7th, 2013. Dennis Overby, who's the science writer for the New York Times, called these the Skittles diagrams. You know, because indeed it did look like Skittles. These are the locations on the sky of all of these stars that are known to host planets now. And of course we don't know about anything in between even, you know, because all we have are these individual Kepler stars that we've been staring at for 4 years. But what I want to draw your attention to is not only the wealth of planets, but their size distribution. You know, these giant planets the size of Jupiter and greater are actually pretty rare among the Skittles. You know, the red one, you don't get as many red ones as you get orange ones and so on. And this is even accounting for the fact that these planets are harder to see. You know, so even though it's harder to detect the smaller planets, look at how often they show up. This is something really crucial about our universe, is actually that small planets are quite common. But it's a lot of hard work. You know, because Kepler is only actually measuring the brightness of the star as a function of time. As you saw in that original video of the sun and Venus passing in front of the sun, stars are dynamic objects. They're very active. The sun itself is rotating with a period of 30 days, presenting star spots on one side and no star spots on another side. Stars flare. You know, and so you can see when you're measuring stars' brightness as a function of time, they're doing all kinds of crazy things. It's the effort of 100 people to comb through this data set looking for the proverbial needle in a haystack. So with say again. Oh, stars for which we did not observe a transit. That doesn't mean they don't host a planet. Oh, I'm sorry, say one more time.
Those white dots were stars which were stared at, so to speak, by Kepler, but no planet was visible.
No planet was detected.
Was detected, but wouldn't if the planets are in a plane, orbiting a plane, I don't know if they always do.
Yes.
Then if it's a random.
Exactly.
Then why would you expect to see fewer?
You would. So for example, if every star hosted a hot Jupiter, they have about a 10% probability of transiting. I know they're very, very close into the host star. So if you just picked a random hot Jupiter and every single star hosted a hot Jupiter, you would only see 1 in 10 transit because of the probability, the random probability. It might be, you know, if this is the star and you are the Kepler spacecraft, the Jupiter might be going around like this. You'd never see a transit. It's only the 1 in 10 that's going like this, where the planet would actually pass in front of the star. So you undertake the statistical analysis where you say, I looked at 100 stars. I saw 10 transit. Therefore, then you can infer something about what is the planet occurrence rate based on the probability of transit for an individual object. And that has...
You removed from that diagram the 90%.
Yeah. Because we just don't know that they're there.
90% of the white dots because they're expected to be white.
I'm almost following. You'll have to ask me more. I'm sure that you're answering a question I know the answer to, and I feel frustrated. I can't.
Of the stars that were observed would be expected to show a trend.
That's for a hot Jupiter. That's for a hot Jupiter. So for an Earth-like planet, it's more like 1 in 100, 1 in 1,000.
Right.
You know, because of the distance.
Right. So I'm saying that you would only expect to find, even if all of them had,
Yeah.
you would only expect to find a 10%. So
Yeah,
even
right.
Even a maximal
Yeah.
diagram that shows you would still have
Oh, yes.
10% white dots.
Yes, exactly so.
Your
Right.
diagram doesn't have 90% white dots.
No.
Which means that you removed all the white dots that you
Yeah.
expect to be there.
Yeah. Okay. Yes. Question mark. Yeah.
In 4 years, you wouldn't detect a cold Jupiter, would you?
No, you wouldn't. But you would detect some. Okay, right. So if you had a period of 8 years, and then you would see half of them, right? Does that make sense? So you wouldn't. So right. So we're only really our completeness only really extends 100% out to planets that present a transit in less than 4 years around the quietest stars. You know, there are stars for which a single transit of such a small planet is impossible to see with just a single event. You would have to stack multiple of them on top of one another. So, you know, for planets that have periods longer than 4 years, this is why the nominal mission was scheduled for 4 years, because it wanted to answer the question of 365 days. You can see why it was scaled to find Earths around sun-like stars. So I'll bring us back to this 2008 transit census, and then this figure was updated in 2013 at this big meeting, annual Astronomical Society meeting in Long Beach, California, which is where that most recent Skittles diagram is from. And I just want to zoom in on a part of it. You know, this is the analog of what that previous figure was. There's no way that people put this figure in papers now. There's just far too many planets. But what I want to draw your attention to is the following. So to scale, here's Jupiter transiting the sun. You know, it's looks like around here is the type of star. This is showing to scale the types of stars that have been known to host planets. And if the sun is right here, the vast, vast majority are smaller than the sun. This is something which is very surprising because the Kepler mission was launched to search specifically for Earth-like planets around sun-like stars. We tailored the mission to look at sun-like stars, but what it was telling us was that planets were much more common around stars that were smaller, and this effect was not small. This effect was extreme, yeah.
Does that take into account the fact that it's harder to see a given size
What a great
planet,
point.
In front of a big star than
Yes.
a small?
There's several reasons why that's true. So first, it's easier to see the transit of an individual planet around a smaller star because the fraction of the area it blocks is proportionally larger. Secondly, it's true because it's more likely to transit if it's closer in. Do you know what I mean? So there's a lot of reasons that are playing into it. So in order to produce the statistical diagram, we have to take into account the number of things we didn't see. So even taking into account the fact that it's easier to see the transits around the smaller stars, there's still more. Yeah, and the answer is there's about twice as many. So this is one of the only two technical figures that I'll show. This is a science grade figure that was published in 2012. This is showing stellar effective temperature, cool stars over here, and hot stars over here. The sun itself is right about 5,800 Kelvin. So here's our sun. And this is showing the number of planets per star within a period range. This was when Kepler was relatively new. This is for periods less than 50 days. For comparison, Mercury itself has a period of 58 days. So this is not yet probing Earth-sized planets in the habitable zone of sun-like stars. What I want to draw your attention to are these different curves corresponding to different sizes of planets. So everything we were sensitive to before Kepler was launched is all down here. The things that are the size of Neptune, which is 4 times the radius of the Earth, up to Jupiter, 10 times the radius of the Earth. So we were swimming around in this kiddie pool, like splashing around in this kiddie pool of, all of these stars have maybe 0.01 planet per star, by which I mean 1 in 100 planets has a star. When we were like, where are all the planets? The answer is they're just smaller. So when you get to planets between 2 and 4 times the radius of the Earth, which at the time, in 2012 was what we could say we were sensitive to, it was still very hard to detect individual Earth-sized transit signals. I want to draw your attention to the fact that sun-like stars are not the most common host to these planets. Rather, it's these stars over here that are much smaller. This is quite odd. So then why, based on the anthropomorphic principle, why are we not residing around a small star? This is something which is sort of very strange, I think. Yeah, I think that's really unclear. Yeah, whether it's flat, because there's still really error bars in between stars which are like 4,500 Kelvin. Also, I should say stars don't stop here. They go all the way down here, like another 500 Kelvin. It's just this diagram stops here because Kepler didn't look at enough of them. Because it was a mission designed to look at sun-like stars. So it looked at a tiny handful of small stars, and there just aren't enough in these bins to even say anything statistically meaningful. But there's probably a lot of planets around here. So this is where other surveys come in, ground-based surveys that I'm happy to talk more about in the question and answer period. But a statement about this plot, which I just think is the takeaway statement, is that sun-like stars are not the most common hosts to small planets. There are these, yeah. Yeah.
Near a small star.
It's weird that we live around a sun-like star.
Right, but isn't that assuming that all these other star systems are not inhabited? Because if they were, it's like somebody living in a small country, seeing all these big countries around in a small country, saying, wow, that's weird, we live in a small country.
Yeah.
That's not weird.
Well, another way.
Statistically.
Yeah, statistically. Another thing would be like, if you were, it would be very odd. It would be very odd if you took a random person in the United States. You picked a random person, and that person was from an extremely rural area. And you would say, what is your life like? And they would say, I hardly ever see another person. And then you would infer, oh, people maybe aren't that common.
If you were a random sun star, and it happened to be ours, that would be weird. But it's not weird that we're here.
I disagree. I think if you were making an assumption about where the small planets are more likely to occur, then arguably we should be around a smaller star than the sun. Now that's not assuming a lot of things. Perhaps, we aren't around a small star because life doesn't is not nourished around small stars. You know, but statistically speaking, yeah, I like an active audience. Okay. Okay, so in 2012, I want to just walk you through the number of planets per star and build you up to this astonishing conclusion about the number of planets per star, which then leads to where is the nearest Earth-sized planet, based on this statistical understanding about where planets occur. So in 2012, you know, lumping in planets between 2 and 32 times the Earth radius. This is basically all planets. Jupiter, as I said, is about 10 times the radius of the Earth. So this is going from, you know, basically things close in size to the Earth to things 3 times the size of Jupiter. How many planets per small star? And the answer was 0.3. So meaning that you have to look at, I've never seen 1/3 of a planet. It means you have to look at 3 stars to see 1 planet of any size. Okay, but that's only going down to 2 times the radius of the Earth. In 2013, we had enough data from Kepler that had been analyzed that we are sensitive now down to planets 0.5 times the radius of the Earth. So going down from 2 times the radius of the Earth to all the way down to 0.5, all of a sudden we found that every single M star hosts a planet. You know, the one thing I haven't made clear is that nature makes M stars so prolifically, way more common in the universe than sun-like stars. So for every 100 stars that nature makes, 75 of them are small stars. By small, I mean the size of half of the sun or smaller, all the way down to 1/10, 3% the size of the sun. So nature makes these stars in profusion, and nature makes small planets around those stars. This is an astonishing conclusion. So it's basically true that every star, I mean, to all extent and purposes, throwing out sun-like stars and all the chaff, you know, every star in the galaxy hosts a planet. I mean, and between 0.5 and 32 times the size of the Earth. Well, what about Earth-sized planets? I mean, that's what people are interested in as far as habitability. Now, if you go between 0.5 and 1.5 times the radius of the Earth, it turns out that there's about half a planet per M star. So now you just have to look at 2. Okay, so this is half, basically, of the stars in the galaxy, for all intents and speaking, 75% of them. Every other one has an Earth-sized planet. Okay, but more conditions are required for life than just a ball of rock to stand on. We want it to be the right distance from its star, such that any water on the surface would be liquid instead of steam or ice. So now you're probing just that thin area around the star. How many of these planets reside in this thin area around the star such that liquid water could reside on their surface and are Earth size? And the answer is 0.15. So now you're looking at about 1 planet out of every 7. Yeah, thank you. So you have to look at 7 or 8 to find an Earth-sized planet in the habitable zone. Well, I just want to introduce you to what our stellar neighborhood looks like. So this is showing, this is a diagram produced by a group at Georgia State. And the nomenclature on this diagram is the following. So the colors are corresponding to the type of star. The red ones are the small stars. You can see how prolific they are. And yet one thing I want to make clear is that not a single one is visible from by the naked eye. We evolved around a sun-like star, and so our eyes are sensitive to light in the visible wavelength range. Because these stars are so small, they're much less luminous than our sun, and they emit light which is much redder, shifted actually into the infrared portion of the spectrum. So they sort of make up our galaxy's silent majority. You can see how populous they are, even in the stellar neighborhood. So this is going about 10 parsecs, maybe 30 light years away. This is our backyard. Look how many small stars there are. Now I want to draw your attention to these numbers. If it has a number after this dot that's whirling around, it means the number of stars. So, there's plenty of binaries and triple systems and so on. If there's a P after, it means the number of bodies where some of them are planets. So this is GJ 581. There was a planet in, I forget whether it was 2010. It appeared and then disappeared. It had a Twitter account. That people claimed that there was a habitable planet around that one. And here in the center is us with our 9 planets. You can see maybe someone is preferential to Pluto. So, here are the nearest neighbors. Now I said 7 or 8 stars is how far you have to look. Well, that's right in here. One of these has it. We just don't know which one yet. The answer is it's going to be another mission that's launched in 2017 called TESS, which will answer the question about which one of these nearby stars hosts the planet. But it's right next door. We just don't know where. You can imagine this is something that astronomers are just scrambling to answer. There's at least 5 missions I can think of that are looking for this planet. Where is it? But the thing is, that particular planet, because of random orientations, may not transit. You know, and so your ability to detect it by the transit method is of course dependent on whether or not the thing transits, including the transit probability. You have to go out to about 31 parsecs. This is still in our backyard. So if that planet, you know, it transits, we detect it 31 parsecs away, that's about 100 light years. So now we're getting to the point of, you know, it would really be something if there was a planet with habitable life on the other side of the galaxy. That would be amazing. How difficult to go there, how difficult to have a conversation. You know, on this planet, at least if you said hello, you know, you said hello, they would hear you 100 years later, and maybe your grandchildren or your great-grandchildren would hear hello back. Or face the invading army. I, for one, welcome our alien overlords. But this is human time scale. You know, that's how close it is.
So even if you say the habitable zone is between freezing and...
Yeah, I'm very loosely defined.
But the star that some of these small stars,
Oh, yeah.
the peak wavelength
Oh, yeah.
is way lower than the peak wavelength from our sun.
Yeah. I'm way ahead of you.
It might matter also for
Oh my God.
light.
Yes, it completely would. I have a whole slide about this. Okay, I'm so excited. All right. So here's sort of the press release. I mean, so Kepler, like I said, was staring, you know, like it was shining a spotlight on only one corner of the sky. Here it is, looking at this part of the sky in our galaxy. You know, based on what we've inferred from the occurrence rates of planets from Kepler, there's 100 billion planets in our solar system, in our galaxy, and that's out of 200 billion stars. This was a result, you know, this very prolific image. Someone used the Photoshop stamp tool, you know, to really evoke in the reader a sense of the like prolific nature of planets. But now we know they're incredibly common. So at the time of this press release, I just wanted to take advantage of what my colleague and friend Courtney Dressing used, the language she used in her press release. So if this is the Milky Way galaxy, and we scaled the entire United States to the Milky Way, and we're here in New York City. I'm sure not very many people in New York would not know we were in New York. That's a thing. We're here in Manhattan. So where would the nearest star be? You know, would it be, to put a little bit in, would it be, you know, where my great aunt lives? She's 95 years old, town of 400 people in Breda, Iowa, halfway across the galaxy. It's hard to get there, you know, although she does love it when I visit. Would it be in San Francisco, you know, where my parents live? I mean, how far away are we talking in the speed of the galaxy? I mean, in terms of the width of the galaxy. The answer is that it would be right on top of us. You know, so if you scaled the galaxy to the size of the Milky Way, the distance to the nearest Earth-like planet is actually just the span of Central Park. You know, so if we were at the Hayden Planetarium, it would be at the Metropolitan Museum of Art. Do I have that right? Then when I looked up Google Maps, you know, you could just take a bus there. You know, so this is something when you think in human scale about how hard it is to travel, this is walking distance. I mean, and probably, you know, if there's, I mean, I like to think it's very hard to speak about how life is actually generated. It's never been generated in a lab. But if you look at the profusion of life on the surface of the Earth, life is certainly not the exception to the rule. Life is the rule and not the exception. And all these extremely, you know, unnourishing environments where, you know, high pressures, freezing cold, it's extremely hard to kill some of these bacteria once you get them going and their little cilia moving, you know, then they are not going to die. It reminds me of this Onion article from 2006 that was on my advisor's door. I remember being so glad my advisor was someone who liked the Onion. You know, this was, what a relief. I was at Harvard, how scary. And you know, a new solar system discovered 4 feet from Earth. Well, if you scale it, it's not quite 4 feet, but it definitely is walking distance. I mean, this is something really remarkable.
Where'd you get that picture of the Milky Way? It was pretty...
This is actually, this one.
Yes.
This is actually a picture of the Andromeda Galaxy. So I think because I'm running short on time, I'll just go to sort of the complications from living around a small star. So I've talked now about how, you know, why is it we don't live around a small star? It's so statistically likely. How odd that we, as a random life process in the universe, you know, chances are much higher that if you take a random being in the universe, given the number of habitable Earth-sized planets, it should be around an M-star. Well, why are we around a sun-like star? The answer to that might be because these environments are incredibly harsh to life. So I want to do a reading from Einstein's dreams. I like to think about sometimes, you know, when I've done a whole lot of work in front of the computer at the end of the day, I looked at a lot of transit light curves. I'm literally looking at a computer. My mom says it looks like the computer is broken because it's full of little windows, full of weird pieces of code. You know, and I go home at the end of the day, and it's easy to forget that these places are worlds. You know, just like our own world. You could walk on the surface of these planets. You know, you could look up in the sky and see a star. It would be half the size of the sun, you know, but perhaps you'd be much closer. Perhaps you would be a being that had evolved to view infrared light. You know, your eyes would have adapted to, you know, to render you viable on the surface of this strange world. These are planets upon which there's a surface, you know, and in order to remind myself of this, I like to read this passage from Einstein's Dreams. If you've never read Einstein's Dreams, I highly recommend it. This is written by a former astrophysicist, actually. He wrote the radiative processes in astrophysics book that many graduate students do, and then he went to the world of fiction, where I think he's just as equally, if not more talented. So this is an entry of one of Einstein's putative dreams from the 3rd of June, 1905. And the reason why I want to do this is because of a phenomenon called spin synchronization. So this is something that happens if you have a body very, very close into a star. It's happened with Mercury. If you have spin synchronization, just as the moon going around the Earth, the planet has been tugged by the star to the point that it's presenting the same face to the star at all times. So while the Earth presents, you know, 365 days in 1 year, for a planet that close into its star, the day is the equivalent of the year. Or perhaps there is no day. Perhaps there's a permanent day and a permanent night. Could life evolve at a location of permanent sunset? Or could it be perhaps that a human life would span a single day? And this is something which is spoken about in Einstein's Dreams. Imagine a world in which people live just one day. Either the rate of heartbeats and breathing is speeded up so that an entire lifetime is compressed to the space of one turn of the Earth on its axis, or the rotation of the Earth is slowed to such a low gear that one complete revolution occupies a whole human lifetime. Either interpretation is valid. In either case, a man or woman sees one sunrise, one sunset. In this world, no one lives to witness the change of the seasons. A person born in December in any European country never sees the hyacinth, the lily, the aster, the cyclamen, the edelweiss, never sees the leaves of the maple turn red and gold, never hears the crickets or the warblers. A person born in December lives his life cold. Likewise, a person born in July never feels a snowflake on her cheek, never sees the crystal on a frozen lake, never hears the squeak of boots in fresh snow. A person born in July lives her life warm. The variety of seasons is learned about in books. And this would be something, if you had life that evolved in a spin synchronized state around a low mass star, and they evolved to the point where they were sitting in their college classes, they would say, how strange, you know, that there are these worlds in which people experience both day and night. How odd. There's the day creatures and the night creatures on our planet, you know, where we only live in this place of permanent twilight. How odd to have there be no light in the sky. You know, and these are things that, I mean, we're on the brink of discovering such worlds. So I guess I'll close. I only have 2 minutes. I'll sort of go to this end slide. I love getting questions, but then I didn't get to all these details. I'll close with this press image of Kepler 62. So it was just this year, actually. It was only a mere months ago that scientists discovered the first, like, really true Earth analog. You know, this is an Earth-sized planet in the habitable zone of a sun-like star. Kepler 62, I forget whether it's E or F. Both of them are very close to the habitable zone. And even though this is something which looks very similar to the Earth and it orbits a sun-like star, the one piece of information that I want you to leave this with is to perhaps use your imagination to conceive of the fact that life might be very dissimilar from us, and life which is very nearby indeed. Thank you. Yeah.
Is that an actual picture of September?
No. No.
How would it get the imagery from the satellite?
Oh, yeah, what a great question. Yeah, all we can do, I'm sorry.
I was saying that
Yeah.
actually sending pictures, I mean, you know, from the surface of Mars, so I was just wondering.
Oh, yeah, I know. This is incredible. I mean, the Mars Curiosity team has done such a great job. You can actually request they point and take a picture of something, by the way, if you haven't done this with the Curiosity rover. So how do you get pictures of other planets like this? Maybe within our lifetime, we would see a picture of an Earth-sized planet around another star. I don't know. You know, I wouldn't bet the house on it. This is an artist's conception. We have rendered pictures. 2009 was the first time we actually took a picture of a planet around another star instead of detecting it indirectly, like with the transit method. But the planets we took pictures of were very strange, in the sense that they were very far away from their stars. You know, because stars are so bright, it's very difficult to see the relatively dim light. It's like trying to see a star in the daytime. You know, the sun, the brightness of the sun just completely washes out the relative dimness of a star. So it's just rendered completely impossible to view the stars until the sun is set. This is the case with seeing a very small, luminous planet reflecting some light from its star next to a huge giant star. It's like seeing a firefly, next to the sun, so to speak. But we have imaged some, and there's hope for imaging them with the next generation of telescopes. But in order to really, imaging some planets, by which I mean larger planets around the very dimmest stars, the stars which are relatively less luminous than the sun. To image an Earth-sized planet on a sun-like star, I'd say 50 years away. And even that's just getting the pale blue dot that Carl Sagan talked about, not this resolution.
How about using a radio?
Sorry, I had a question.
Yeah.
And if you look at just the black body temperature of the Earth,
Yeah.
It's a little bit too high.
Oh, yeah. Right?
So
Yeah.
even if you are in the right zone, whether a planet is inhabitable or not depends on other things. Like
Oh, very much so.
Will we be able
Yeah.
to see those characteristics in
Yeah.
foreseeable future?
Yeah.
5-10 years?
This is a great question. So actually, it's true that the Earth doesn't reside in the sun's habitable zone. It's actually slightly too cold to be habitable. So the atmosphere on top of us, including the greenhouse effect, which we humans have kind of driven to be a bad thing, was originally a good thing. It warms us up to be just the right temperature for liquid water. But in terms of, if the star resides in the habitable zone, what does that really mean? How do we confirm that it's habitable? There's a couple ways that people have talked about doing this. I would say the most promising one is the following. You identify a planet that transits its host star. And then any planet which we think is habitable and which isn't, like the surface of the moon, has an atmosphere around it, which is providing this pillow and buffer for life to breathe oxygen and so on, and not be swept out into space. The atmosphere also provides us a little bit of gravity, but not very much. So we would wait for this planet to transit in front of its host star. And then, so the photons, the particles of light traveling from the sun, from the star, would not only be stopped by the bulk, rock of the planet, they would also be stopped by the atmosphere in certain wavelengths. So our own atmosphere permits light of certain wavelengths and forbids light from other wavelengths. So what you would do is you would look at the planet's transit in multiple wavelengths, and the planet would physically appear bigger at the wavelengths in which the atmosphere was not permitting the light to get through. In this way, you could detect, so for example, ozone, which is something which is not produced abiotically. Only life produces ozone. You would look at a bandpass sensitive to ozone, and you would look at another bandpass. And if the planet appeared bigger at the wavelength corresponding to ozone, you would infer ozone is present. And this is a so-called biosignature. But the only other way, and you would say, well, this can't be produced abiotically, and then there would be an argument in many conferences and many articles in the New York Times about whether or not you could interpret it. I brought this up recently at a big meeting for exoplanets, and I was wondering if human beings would ever really be satisfied until we held like a creature, in the palm of our hand from another world. And indeed, I think that's probably the next step of maybe not my children, but my grandchildren or their grandchildren, of going to another world. It's what I know I hope for eventually for humanity.
But in the short scale, this ozone signal.
In the short scale, this is the best. This is the best hope.
Short scale means 5 years or 6 years?
Short scale means after the launch of JWST, which is probably 2020 if the House doesn't remove our funding again. Then JWST has to be launched. Then there's an argument about how much time exoplanetarians should get versus other folks, and they have their own right to JWST. Then we have to find the one planet that we will put all of our eggs in this one planet's basket and stare at it. This is humanity's best instrument, the most sensitive instrument, and even then we'll have to stare for hundreds of hours to resolve this feature with ozone. And I think my guess is we'll find this nearby planet, it will have an atmosphere, the atmosphere will contain ozone because everything else seems to be, the rule rather than the exception, and then 2025, 2030, that's my guess.
On that note, let me propose to continue discussion during the reception. So thanks, Ballard.
Thank you. Yeah, it was a pleasure.